James, what should I do first?
What's the value? We have to get the value of inverse tangent of x at 0.
You're getting the value of inverse tangent of x at 0. Good. Okay. So you want to do f of 0, and that's going to be tan inverse of 0, which is what?
0.
0. So then after you do that, what should you do next? What should you write out? Yes?
Differentiate our tan.
Yeah, so you know f of x, we're doing number 7 here. F of x is equal to tan inverse, that's a big inverse of x. So what's f prime of x going to be? Who's got f prime? Yeah, right, what is it?
1 over x squared plus
1 plus x squared, correct. And then what's another way to write that, because we're going to have to keep on repeatedly differentiating? 1 plus x squared to the negative 1. So f second derivative of x is going to be negative 1 plus x squared to the times what? Times 2x. Excellent. Is this going to get nasty real quick? Yeah, this is going to be really nice, because what do you have to apply now when you do this?
Chain product.
Yeah, you're going to be like, yay, it blows up on you. So you end up with 2, the derivative of the first, right? The derivative of the first times the second plus what? Plus the first times the derivative of the second. Okay. Yeah. F prime of 0, what's that going to be? 1. What's f double prime of 0 going to be? 0. What's f triple prime of 0 going to be? What is it?
Negative.
Is it negative 2? People agree with that? Yeah. Okay, I'll go with you on that. So, if you really wanted to, do you want to do one more differentiate? Did anybody do the fourth one?
I did. It asked for the fourth.
Oh, it asked for the fourth. Oh, it does ask for the fourth? I thought it said degree n. Oh, and n equals 3 and 4. Oh, I'm sorry. That's a lot better than I thought. I thought they wanted you to actually write out the formula for this thing. And I thought if yesterday's thing was a challenge, this one would be horrible. Okay, so yeah, f4 of x. I'm not going to do it out, but can someone just tell me what the fourth derivative evaluated at 0 is? Who has an answer for that?
0.
Who got 0? Raise your hand if you got 0. Okay, that's some good agreement right there. So if we're actually going to write this Taylor polynomial, if we're going to write this, let's write it for
negative a.
Hold on. Let me finish the actual words coming out of my mouth. I know you're really eager to answer. I'm very proud of you. Just give me a second, okay? So the Taylor polynomial 4 of this thing, what are we going to call it? It's going to be what? Who wants to read it off to me? Or who has it in their notes? I can check it right now. Who has it by the pattern? And you ended up with this right here. And what did the book do?
The book
cancel things out, right? Yeah, they'll do that when they're expressing something, so they don't. So it's going to end up being x minus 2 over 3 factorial, which is 6x cubed, which does turn into that right there. Nice. Good. How do we feel about that? Yes, Henry.
If you go up.
So what did you do to attack this? You did the what? What'd you do?
I looked at it and was like,
Okay, you looked at it and said, I don't know what's happening right now. Okay. So here's the thing. Right now, why can't you just do that limit right there?
Because
it's weird and strange, and it's not quite strange. So they're saying instead of using cosine, what should you use?
The Taylor approximation.
Yeah. So essentially, what you're doing is you're just taking this and where are you plugging it in? For cosine. So you're doing this limit. You're doing the limit as x goes to 0 of 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial all over x squared. What happens there? What does that turn into? The limit as x goes to 0 of what?
1/2 minus x over 4 factorial.
We get x squared over 2. Let's just do it out. Minus x to the 4th over, what's 4 factorial? 24?
Yeah.
All over?
X squared.
X squared. So what does that simplify to?
1/2 minus x.
Yeah, it simplifies kind of nice, doesn't it? Well, it simplifies. Yeah. It simplifies to something that you can do a limit of kind of nicely, right? So what do you end up with x? You get the limit as x goes to 0 of x. How many? You get 12 of them. So 11. What do you end up with? 20. Multiple by 12, right?
Wait, what?
Wait, what? Wait, I'm just doing this too many things at once here. I understand. So bring up the x squared. I understand. So you're saying turn it into just. I understand that you can see this. I just want to make sure we do this out over 24x squared like this. Is that correct?
Mm-hmm.
Nice. So what does this turn into? Well, it turns into 2, and you know that that goes away, but then that goes away, and that turns into a squared.
Mm-hmm.
Is that correct?
Yeah.
End up with a, yeah? Did I multiply something wrong? What's wrong?
No. Why is it 24 times
4 factorial.
4 factorial is 24. It was 4 factorial over here,
2? Yeah.
so that became the 24. So what does that turn into? 1/2 minus x squared over 24. What's that going to go to? 1/2. So there's a practical application of a Taylor polynomial being used to approximate a given function at a certain place. It's kind of cool.
Really cool.
It's kind of, I think it's kind of cool. Yes, Brendan, one more. Infinite number of terms. So for example, what was this? What was this thing right here? What is that?
Taylor approximation of cosine.
Taylor approximation of cosine around what? Turns out to be around everything, right? Turns out it doesn't matter where you take it, it's actually come out to be this. But here's the deal. This is around 0. That's what we looked at yesterday. And what's going on as you go down further and further? What's going on? You're increasing the degree, but what does that do for you?
It makes it more accurate.
Makes it more accurate.
And each individual term is going to be smaller.
Yes, each individual term will be smaller. That's great. But it will make it more accurate. So basically, it's going, for this one, it's going up and above, it's going down, below, down, below, down. It's kind of cool. It's kind of neat. So what you end up with are these 3 big ones right here. And we did cosine, and we did sine, sorry, we did e and cosine yesterday. You can do sine pretty much exactly the same way you did cosine. These are the 3 hugely important ones that you must memorize. Must know these cold. These must be, I'll say, automatic recall. These must, yeah, total recall, the original movie, not the current one, which was not as good as the original. Okay, you must know these. You must know these, because what's going to happen is you're going to be asked to do things with these series right here that if you don't have instant recall, it's going to be a pain in the butt. You can't derive these every time you need to use them. These are just automatic. These are vowels for this section. For example, what might you do if you know sine x and cosine x? What can you start constructing? Start constructing all the other trig functions. You can start constructing other trig functions, for example. What is this? It's an for which? E to the x. Right, exactly. What about this one right here? What's this one? Sorry, I'll move it over. Which one is that? Is that for cosine or sine? How do you know it's cosine? Yeah, because you have even. This is an for cosine x. Exactly. Nice. It's important that you know them. Important that you can recognize them. It looks visually really complicated, but oh, that's just cosine. Cool. Very cool. So this is almost identical to what we looked at yesterday. What's the only difference between this and what we looked at yesterday? It goes on forever. That's it. It goes on forever. That's it. The only thing that changes is it now goes on forever. So this is the Taylor series for f of x about 0. About 0. Well, does it have to be around 0?
No.
No. It could be around what instead? An a value. And what's the only thing that functionally changed here? Instead of 0, you wrote a, and instead of x minus 0, you have x minus a. This one is just a subcase. If you plug 0 into this, what do you get? That one. Yeah. Nothing has changed. And again, what's the only difference between this and what we saw yesterday? Ellipses. Goes on forever. It's very exciting. Okay. So what is this right here? What is this? Tell me what that is. Here. So what's going on here? Look. Here's the function ln(x). You see it right there? Here's the function where it equals 1. You see all these blue lines? You have P5, P6, P7. That is the Taylor series approximation of degree 5, degree 6, degree 7, and degree 8. Right? As the degree goes up, what happens to the accuracy of how close? Do these bend towards or away from the function? They bend toward the function, right? The challenge, though, is this. Is ln(x) defined for anything 0 or less? No.
No.
Look what happens over here. The function ln(x) goes like this, but what do these functions do? Look what happens after you get beyond 2. What happens?
They either go up or go
They
down.
spike up or they spike down. They spike pretty hard. Inside the interval of convergence, though, as the degree goes up, what happens inside this interval of convergence? It gets closer and closer. Like if you zoom in, you'll notice that here, these blue lines are going to go down. Not lines, these blue functions are going to go down, and they're going to go, I think, down. I think it goes up above. You have to zoom in real far. The idea is inside the interval of convergence, as the degree of the Taylor series increases, the Taylor series gets closer and closer and closer and closer to what?
The actual function.
The actual function. But what happens outside of 2 and outside of 0?
It's getting far away.
It doesn't work. It doesn't converge. It doesn't converge. Mainly because in order to find out the distance between two things, you have to have two things, right? Is ln x defined less than 0? No. So what's the distance between something that doesn't exist and something that exists? Undefined. Doesn't converge. Yes, Henry. Let's look at another one. What about this one right here? What's the only thing that changed right here? Do you have a question, Henry?
Yeah, why is the Taylor, if the
So we have f of x is equal to ln of 1 plus x. What's f prime of x going to be?
1 over 1 plus x.
So x plus 1 to the, so we f double prime is going to be to the negative 2. Is that correct? Negative, yeah, thank you. Thank you. So then you have f3 of x is going to be 2 times x plus 1 to the, hey, it's not blowing up on us at least. Magical, yay, nice, nice, nice. So what's f of 0? 0, right? Yeah. I sometimes get this wrong, so help me out. So f prime of 0 is going to be 1. F double prime of 0 is going to be what?
Negative
1. And what's f of 3 going to be?
2.
2?
Yeah.
Is that it? Nice. Okay, so if we actually wanted to write the Taylor polynomial here, what's the first term going to be? It's f of 0, right? It's around 0. So it's going to be 0 plus 1 over 1 factorial x. Is that correct? Plus negative 1 over what? X squared plus what? Plus 2 over
3 factorial
x cubed. Now, if we were going to write this out properly, what would we need to actually write out next? Maybe we need the an term here. Anybody come up with that an term? One really important thing you need to get your mind around is we're not always going to do things properly the first time. You very rarely do things properly the first time. You need to start somewhere. Starting is the key, and having the tenacity to finish. So where do you want to start if it's not at 1? Start at 0, and this is 1, and this is 2, and this is 3, so forth, right?
Yeah.
So does that work having it to the n power?
N minus 1
It should be n minus 1 or n what?
plus 1.
Does it matter? Why do I like n plus 1? It's really petty. Yeah, I like keeping things positive when I can. It's fine. It's fine. N plus 1. But what else are we missing? So it goes 1, then 2. What's the next? It's going to be. So what do we have to put up there?
1, 2, 3.
What's the next thing right here?
N minus 1.
N minus 1 what? Factorial. Nice. Excellent. It is n minus 1 factorial. Now, the thing is about the interval of convergence, you could do essentially the same exact work as what we did before. Do you remember what the interval of convergence was for ln x? Do you remember what the interval of convergence was for ln x? It included 2, but it did not include 0. It did not include 0. Remember? We did this out. It doesn't include. It just doesn't. Okay. It doesn't. Now, what's the relationship between ln x and ln x plus 1?
Shift.
All it does it change anything other than shifting? No. The functional characteristics of the function stay the same. It's just moved 1 to which direction? 1 to the left. So if the only thing that changes is the position of the function 1 unit to the left, what happens to the interval of convergence?
1 unit to the left.
1 unit, exactly. You just subtract 1 from everything and what do you end up with? There's your interval of convergence for ln of x plus 1. So that's one thing you know that the interval of convergence, hold on, for ln x is 0 to 2 containing 2 but not 0. If we're changing that function, we're just moving it 1 to the left. Therefore, what happens to the interval of convergence? It just moves 1 to the left. That's it. Yes, Jesse, your question?
3.
Oh, yeah. Kids in the back. So we now know that 1 plus x to the third is going to be equal to 1 plus 3x plus 3 times 3 minus 1 over 2 factorial x squared plus 3 times 2 times 1 over 3 factorial times x cubed plus 3 times 2 times 1 times 0 over 4 factorial times x to the fourth. Does this theoretically keep on going?
Yes.
But why do I not care about the rest? These are all 0, and this right here is just applying the Taylor series, the general definition of a Taylor series, to 1 plus x to the p power. But what does that tell you? 1 plus 3x plus 3 times 2 over 2 factorial x squared plus 6 over 3 factorial x to the third. Can you simplify that a little bit? Yeah, what's that turn into? 1 plus 3x plus squared plus 6 over
Just x cubed.
just x cubed.
Ooh, neat.
There it is. It's kind of cool. So guess what? 1 plus x cubed is equal to that thing using Taylor series. I thought it was pretty cool.